Good morning, everyone, and welcome to our third PSYCHE workshop on the purification of syngas. Today we will have 4 lectures by 2 invited speakers and 2 project partners, followed by a discussion and brainstorm session. Before we start, I would like to stress some points of attention for the workshop. So first of all, please all turn off your cell phones and put your microphone on mute so we have no background noise. If you have a question or point of discussion, please use the chat function to bring it up. I will combine all questions. Small questions can be covered after each presentation, and bigger questions and points of discussion will be addressed during the brainstorm session. Thank you all for taking this into account, and please enjoy the workshop. Our first speaker today is Professor Kevin van Geen from Ghent University, who is also the coordinator of the PSYCHE project. Professor van Geen is specialized in thermochemical reaction engineering in general, and in particular the transition from fossil to renewable resources, including the thermochemical recycling of plastic waste. He will give an introduction to the PSYCHE project. So Kevin, the floor is yours.
Thank you, Elizabeth. I will share my screen. Voilà. So, of course, welcome to this workshop. And this workshop is part of the PSYCHE project. The PSYCHE project is all about plastics. And as you can see, the world's plastics production is still increasing. In Europe, there's a small decline, but still it's very high. And recycling is high on the EU agenda. Next to plastic production, of course, you have product manufacturing, you have use, and then you have different options of recycling. It can be under the form of energy recovery, it can be mechanical recycling, it can be chemical recycling. And if we do that, then we can try to reduce our CO2 footprint of the whole value chain. The central piece of all these elements is also the energy aspect, and that's also partly discussed in this setup series with what can we do, for example, with renewable electricity. If you look at the plastic waste recycling, then we see that there's a gradual increase, and that today that we can say that recycling has outpassed landfill. Also, energy recovery is heavily done, but of course, energy recovery results in substantial CO2 emissions. So the objective also of PSYCHE is to further increase recycling and limit energy recovery, and certainly not landfill. To give you some numbers, then you see here some end-of-life emissions. Then you see that really by incineration, which is the orange bar, you really have substantial emissions and of CO2. You can also see that during plastics production, that the main part to work on is then the conversion of naphthas or ethane to monomers. For example, options like using renewable electricity, electrification of steam cracking furnaces are things that are pursued, not also by the groups that are part of this project, but also by other groups in the world. So if you can avoid combustion, then we can make a step forward and drastically reduce emissions related to plastics production. Who are the partners? So we have University of Ghent, which is my home institution. Then we have UC Louvain with Juraj de Wilde. We have the University in Lille. We have CNRS and CERTECH. All these partners, they work together on this PSYCHE project, which got funding from Interreg, which is from the France-Wallonie-Vlaanderen Interreg program, and the funding is 2.6 million euro. The central piece of this project is 2 parts, so the pre-treatment and gasification of plastic waste, and then the Syngas Purification and the Fischer-Tropsch production of olefins. So the focus as end product is really here on olefins. Next to that, of course, we have communication and education being part of the project. The value chain in a nutshell or in a short overview can be seen in this slide. So we start from unsorted plastic waste. We look at different pre-treatment methods. After pre-treatment, we can do gasification, and we do this in a vortex reactor technology that I will discuss later on. We go then to Syngas Purification and Fischer-Tropsch production. So really want to produce useful base chemicals, olefins, for the chemical industry. If you look at the slide from right to left, so we have plastic waste, then we have the pre-treatment, we have the gasification going to syngas, which is a mixture of hydrogen and CO. And then, because there also are some impurities in plastic waste streams like chlorine or other components, there needs to be some purification of that syngas before it can enter to a Fischer-Tropsch plant, and where that syngas is being converted to, for example, 1-hexene or lower olefins. So let's go look at that a bit deeper at the pre-treatment step. So we know that additives improve the physical chemical properties of plastics. And you have a whole range of different additives that are being used: functional, reinforcements, colorants, fillers, and so on. However, for recycling, they do not make it easier. And that's why, well, removing them is not that obvious. So in the PSYCHE project, of course, we have to be selective on the pre-treatment steps that we focus on. We focus with Steven and Meester here on solvent-based techniques, not so much on mechanical and devolatilization, but we look at conventional methods, pressure-assisted method, and solution precipitation. And for example, you see here a review paper that discusses all these options, which has been recently published, with a complete review of solvent-based extraction techniques for plastic waste. The objective of that part is physical-chemical treatment of plastic waste via various extraction methods. We also look at different types of additives that we would like to remove. And of course, in the end, we are optimizing that pre-treatment. And I can say that Steven has made very nice progress in that part. Then we go to the gasification part, which is done in the vortex reactor. And a vortex reactor is a bit of a special reactor. It's a sort of fluidized bed reactor, but not like a classical fluidized bed reactor. In a classical fluidized bed reactor, you have relatively low gas velocities because you basically have to work against gravity. And this means that the gas velocity at the bottom is rather small, because otherwise you have particle entrainment. You have a dilute bed in these technologies. And if you look at our gas solid vortex reactor, it works a bit like your washing machine or your dryer, where you have the particles in wet, and they basically are driven by the black arrows, which come in from the side and which make that the particles start to rotate at a very high velocity. You can have very high gas inlet velocities, so gas flows, which results in sometimes even a packed bed. And the advantage is also you have very short gas phase times. This means that you can also avoid secondary reactions substantially. Overall, you basically end up with an intensified process, also with a smaller reactor. And you see here different reactor technologies that we have currently available in our group. And the one on the right is, you see also different parts here in the bottom. You see that it's not only a nice drawing, but you see here also in the bottom the different parts of that vortex reactor technology. So what happens is we have solid plastics. We go to the reactor environment via an extruder. So that's the plastic melting. That liquid is being fed to this vortex reactor where you have pyrolysis and gasification going on. Then you end up with the char and some remaining tar that you have, but also mainly vaporized and cracked gaseous products that in the end are mostly CO and hydrogen. And by simple separation, we are able to remove the char in a cyclone, and in this way we end up with the syngas that is then can be fed to the Fischer-Tropsch unit. What do we try to do in this project? We try to do numerical and experimental investigation of plastic waste gasification in this gas solid vortex, but we try to do this with the help of computational fluid dynamics. And computational fluid dynamics is not so much called for directives, but we really like to use it for design. And I think that's one of the things that we have done in this project, is to design this vortex reactor to make it more suitable for gasification. And finally, we end up with the olefin production step. And of course, you can do this step sort of randomly. You can test a huge number of catalysts and then screen them and come up with the best design. In the PSYCHE project, we try to use model-guided catalyst design. So this means that we try to gain insight in the chemistry of the Fischer-Tropsch step. We try to relate that back to catalyst properties. And when we understand how those catalyst properties affect the final selectivities, we can use that in our models and perform scale-up. If you look a bit closer, then in the end, what we do is we have the reactor model equations. In those reactor models, you basically have the detailed chemistry, which is shown here as the microkinetics. And that really accounts even for things happening on the pellet scale. And by integrating all these phenomena on the full reactor scale, we basically can predict in advance what will come out of this Fischer-Tropsch reactor. And then, because we have some variables in this kinetics which account for the catalyst, you can basically optimize the whole system and come up with optimal catalysts. Obviously, it's a challenge to account for all these catalyst descriptors into the model. But thanks to the group in Lille, then and CNRS, we really have very unique data that we can use to validate this whole system. And of course, that's what you need to, in the end, to become predictive. So now we have models that are able to predict the experimental data, but we also need to be predictive. So this means that we have to be able to account for changes to the catalyst. And this is still the step we have to take. And taking us back then to today, of course, if you do all these conversion steps, then today what we use is typically we use combustion to provide the energy for all these processes. If it's an ectothermic process, then you don't need a lot of energy. But if you have endothermic processes, then you actually need energy. And what we really try to do now is to take this one step further, is how can we further reduce CO2 emissions, or how can we even use CO2 in our processes. And in this way, we hope that by electrification of this whole system, we can further bring down emissions of the whole system. Of course, this only works when you use renewable electricity. If you use electricity from the current grid system, then this is gray. And of course, this results in additional emissions. And sometimes you can end up with worse situations than actually today. But we'll have some examples by Giorgio Stefanidis here today, where he will go into plasma technologies and see how we can use that to drive this chemical process. So with this, I want to acknowledge all the sponsors and all the partners that are involved for making PSYCHE a success. Thank you, and I hope you enjoy the talks.
Thank you, Kevin, for your introduction to the PSYCHE project. Our second speaker today is Timothy Musselmans from the company Cameron Carbon. After graduating as a bioengineering chemistry, Timothy joined the Application Engineering Department of Cameron, where he currently holds the position of Application Engineering Manager for Europe, the Middle East and Africa for the Cameron company. So Timothy, the floor is yours.
Okay. So I will speak a little bit about activated carbon purification. What are the possibilities of activated carbon? As already introduced, I'm working for the company Cameron, which is part of the Calgon group. And we are a global supplier of activated carbon products and associated services. For example, also recycling of used activated carbon and mobile adsorbers. Additionally, there is also on-site technical support. We have our own R&D facilities and so forth. And we do specialize in activated carbon, and we do as well some filtrates through our branch in France. So some quick numbers, maybe also noteworthy is that in 2018 we were acquired by Curere Chemical Group, and since then we are the environmental services division, although we do much more than just environmental solutions, we are also very active in purification of gaseous streams, liquid streams, and so forth, but more about that later on. So in Europe, we're called Chemviron, but everywhere else in the world, we are called Calgon Carbon. As I already said, we are a global company, so that's also quite interesting because some of our projects start off in one part of the world and then they expand further and further and further through the whole globe. And so we are in a position to basically follow the needs of our customers from one area to another area. Maybe interesting to notice is that most of the activated carbon production is focused in United States and in Asia. There's very limited production anymore left in Europe, as in a lot of industries. But we provide our recycling services through over the whole world. So not only in the US, but very strong as well in Europe. That's probably our main activity in Europe is recycling, and as well in Asia. Okay, so where can you use activated carbon for? When you look at industrial processes, we can do a lot of things with activated carbon. Can be purification of emissions to the air that are developed in a production process, or could be even, for example, in refineries or similar itself, purification of liquid streams, of gaseous streams. I'm thinking, for example, purification of natural gases, other pure gases in refineries that are done with activated carbon. Typically, it's the removal of the final concentration of the impurities for large concentration ranges. People tend to use some things like scrubbers, for example, but there as well, these scrubbers, they operate with liquids, and these liquids need to be regenerated. They can be fouled, and the fouling can again be removed with activated carbon. So we are present in quite a bit of different applications, just alone even in the refinery. Next to the chemical industry, we are also present in drinking water, purification of wastewaters. A lot of food products are also purified with activated carbon to remove colors, to remove pesticides, other unwanted byproducts. Those are all things that can be done. And next to that, obviously, the company started out with making activated carbon for gas masks for the military. That's still an activity that's really important for Chemviron, which we still do to this day. We have a very unique set of impregnated carbons for that, not just for military applications, but as well for personal protection, etc. The typical gas masks that most of us probably already know. And a final one is activated carbon cloth, and that's really sort of a textile activated carbon that is used, for example, as well in medicinal applications to accelerate wound healing from burns or similar. So in total, there's more than 600 applications that we are involved in, left or right, and that we know of. The number still grows day by day, I would say. And the benefits that we see that we can learn in one application, we can also bring to another application. So that's always quite interesting for us as well. Maybe a final word on how do we operate. Well, we produce our own activated carbon. We also produce some filtrates. Some in liquid phase, both sometimes are required. In gaseous phase, obviously, there's no real use of filtrates. But our activated carbon, together with the mobile adsorption systems and our reactivation, those are the key components where we try to bring a complete service to the industry. In addition to that, our production facilities are in support of that, and we also have dedicated support services with field technicians, but also our R&D labs that continuously develop and improve processes for customers, and our application engineering division as well, where I'm a part of. We have seen in the previous presentations that incineration emits a lot of CO2, and obviously that's also something that came to our attention many years ago already. And that's why we focus a lot on the reuse of activated carbon, because activated carbon, and I will talk a little bit more deeper about the material itself in a moment, the material itself has a limited adsorption capacity. So it removes the contaminants and it stores it inside its porosity. So when that material has been exhausted, it has to be taken out, and either in the past it was landfilled or incinerated, but more and more and more we are recycling this material, and in Europe we are doing that already since the end of the 1970s. We recycle the material thermally, where we destroy the impurities that have been adsorbed inside the pores of the activated carbon, and we reinstate the adsorption capacity of the material. So it's like a closed cycle loop, if you want. You see there on the slide an example. So we go and pick up the used material, we bring it together in a pool, we do the quality control, obviously, on all spent materials that arrive. We then apply again a sort of activation process, which is a thermal process at high temperature, after which we recover reactivated material, where we aim to have the same performance as the original material. And I have to say that most of the time we succeed into this. Obviously, in the whole handling, you always have a little bit of loss. So there is a little bit of makeup that's been added to the system, but that's a very little amount overall. And then customers get back reactivated carbon, which they tend to use. So it's really like a closed cycle. And the overall benefit expressed in CO2 footprint is that the CO2 footprint of this reactivation cycle is 5 times less compared to the solutions whereby people have to incinerate their used activated carbon. So then I move to the next point. What is in fact activated carbon and what does it do? Well, activated carbon is basically a very amorphous form of graphite, which renders the material highly porous. And not only that, it also establishes a very wide range of pore sizes. So what you see there on this slide is basically the planes represent graphite platelets. Graphite is a almost flat structure that is arranged amorphously, so at random, inside the granules or the pellets or the powder of activated carbon, whatever you're using basically. These platelets, they can be connected through aliphatic dislocations or aliphatic chains from one chain to another. But it's really this at random structure that gives the high porosity of the activated carbon. So it's not really like a molecular sieve or a zeolite where you really create a definite range of pore size where the molecules have to migrate through. This is a very random structure where molecules diffuse into, and then they are retained through van der Waals forces inside this structure. Now, to give you an idea about the porosity or the surface area internally inside activated carbon particles, if you would take 5 grams of activated carbon and you would basically cut it open and fold open all of its internal surface area, you would cover with 5 grams an entire football field. So that's the amount of internal surface area that's available for purification, or in some cases also for reactions to take place. Now, how does the molecules are retained inside the activated carbon? Well, that's through adsorption, so that the molecules do not change on itself. They are simply diffused inside of the activated carbon, and then these molecules will be held in place through van der Waals forces, London dispersion forces to be even more precise. It's thanks to the high internal surface area that a lot of interactions are developed with the molecules or the impurities to be removed, and thus they are retained inside the porous structure of the activated carbon until they are either incinerated or until a reactivation is performed on that spent carbon. Next up, this is a sort of a cutaway view of how an activated carbon would look like on the inside and how adsorption takes place. So to give you an idea, in particle of activated carbon, you would find about 35% of carbon skeleton, 25% of transport pores, and about 40% of adsorption pores. This is for activated carbon that's made out of coal. If you use another starting material, you get another ratio of skeleton and adsorption and transport porosity. Now, this ratio is quite important because on the more viscous streams, you won't have more transport porosity, whereas on gaseous streams, where diffusion is quite rapid, you do not need a lot of transport porosity, and thus you can aim for more adsorption porosity. So on the left hand of the slide, it's, like I said, a little bit of a cutaway view where you can see the graphite platelets. These are the thick bars, basically, that again are more or less randomly organized. The small lines are aliphatic dislocations that can interconnect these graphite platelets. And the areas in between these graphite platelets, which are closely spaced together, are typically the areas that would be the adsorption pores. So you can see here in this representation, the gray area is actually the adsorption pore sites. So it's not really a pore, it's really a sort of space where adsorption occurs. But as activated carbon started to be developed or was more and more investigated in the beginning of the 20th century, people were still talking about pores, and it was only in the later part of the 20th century that it was conceived that in fact it's not really a pore, it's more of a surface site that's present. So again, between these two platelets, you can see the gray area, that's where adsorption would occur. And where the distance between the platelets is quite large, that's basically an area where the adsorption forces are weaker, and thus that's a porosity that would be effective in the transport of the molecules. And it's that combination of adsorption and transport which is quite important, as it is overall a mass transfer exercise that takes place in adsorption. So this is a little bit quickly explained how activated carbon can retain molecules inside its structure. Now, if we look at the different forms of activated carbon, as I said already, different raw materials can be used to produce it. They will also generate a different porosity structure, but we can also develop different ways of how the carbon would look like. For example, we have the carbon cloth, which is more for wounds, medicinal applications, and also some military applications. But you also can make activated carbon in a powdered form, a granular form, or an extruded form. Powdered activated carbon is something that is typically used in labs or in batch-wise liquid applications, whereas granular activated carbon is used in liquid applications as well as gaseous applications. Obviously because of pressure drop reasons. And also for these pressure drop reasons, in gaseous applications, we use extruded or pelletized or cylindrically shaped activated carbon. That's really where pressure drop is the most limiting factor for the overall treatment. So different forms exist, different raw materials exist, and thus the choice becomes based on what we need to remove, what are the conditions, what are the constraints for the end user, pressure drop or certain performance. We will make a choice on what can be the best solution in that case. A little bit more about what activated carbon can remove now. Well, activated carbon on itself, as I mentioned, is made out of graphite platelets that are randomly organized. Now, graphite is a very apolar hydrophobic molecule, so it's quite logic that the molecules that are preferably removed with activated carbon are also hydrophobic in nature. And basically, the flatter their 3D structure is, the better they are retained. So molecules with multiple aromatic rings are typically very effectively removed. As well as larger molecules, the bigger a molecule becomes, the more interactions it can make with the surface of the activated carbon. And thus, as a consequence, the stronger it can be retained inside the pore structure. Other groups that are quite important as well when evaluating molecules can be, for example, halogen groups, because they add a lot of molecular weight, if you'd like, to the structure. And they have a very large electron cloud, which can also aid in making a lot of interactions with the material. And next to that as well, if there's hydroxyl groups present or thiol groups, ammonia groups, and so forth, that can also all help to better retain a molecule on activated carbon. Now, there's several compounds which are not falling into these categories, like, for example, smaller molecules such as formaldehyde or hydrogen sulfide. But for those, there are also solutions available. Again, this is then more when it's a little bit more of trace contamination removal, a few hundred ppm Vs, for example. At very high concentrations, people would maybe look at scrubbers. But at a few hundred ppm Vs to down to a few ppm Vs, impregnated carbon can be a solution for removal of these compounds. And impregnated carbon is basically the activated carbon, so the porous structure of the activated carbon, which gets impregnated or filled with an active agent. Typically, it's a salt that engages into a chemical reaction with the impurity which we would like to remove. And the reaction product is thus retained, either because the molecule has become bigger through an oxidation, or the molecule simply is associated with this chemical salt and thus is retained. Molecules that as such are very effectively removed, as for example hydrogen sulfide, ammonia, carbonyl sulfide, mercury as well, phosphine, arsine, and the list would go on a little bit further. In these kind of processes, temperature, humidity, pressure, and concentration as well of other compounds can be very important factors. And these type of impregnated carbons, we find them used in a variety of applications. For example, the activated carbon you find in gas masks are typically made out of a diverse set of impregnated carbons aimed for the removal of different toxic compounds. For example, in the above list, phosphine, arsine, ammonia, hydrogen sulfide, and so forth. But it's not only in these gas masks you find these impregnated carbons, also in the industry. For example, in natural gas purification, mercury is an important contaminant as it affects the cooling system. And thus the mercury has to be removed, and that's typically done in large fixed bed adsorbers at high pressure, 30 bar, 50 bar, where mercury is removed to less than 10 nanograms per standard cubic meter in these cases. Also, sometimes people are looking at a cascade of different molecules to be removed. And then what we simply do is we will combine different types together, either in the same adsorbers or in separate adsorbers, in order to provide a full purification. So here you see on the slide an example of a fixed bed adsorber, but sometimes this is not really necessary because people can also use mobile adsorbers, and that's typically something that is done, for example, for piloting or for remote applications, or there is also the possibility to do this full scale. A lot of customers nowadays are using this full scale continuously because it avoids capital investment. And also it's quite nice as people do not no longer need to touch the activated carbon itself, because the material will always be black and it will always have a little bit of small amounts of dust associated to that. Now, by providing the activated carbon in a closed environment, a closed vessel that's both the transport vessel and the adsorber in one, we're able as well to remove that inconvenience for customers. And these things, the two adsorbers that you see here are examples that are used on purification of either biogases, so biomethane, or biosyngases as well, either in the production of electricity or in the production of the pure gas itself. Give you an idea about the size and what we're talking about. These type of adsorbers, they're capable of handling up to near half a bar gauge. And we're talking about flow rates that go from 400 to 3000 actual cubic meters per hour. And so these type of adsorbers or these sizes are able to accommodate the use of around 50 tons of activated carbon per year up to several hundred tons of activated carbon per year. The smaller one can hold 2 cubic meters of activated carbon, whereas the bigger one is typically filled with around 18 cubic meters of activated carbon. And these are adsorbers that are approved for uses in, for example, biogas, biomethane, or biosyngas, for that matter. Now, I have something as well added on the purification of syngas. For example, what kind of contaminants do we see in different syngas applications, and what can be removed? Well, if the syngas is produced out of a sort of biomass, we sometimes have requests for removal of hydrocarbons, for example, terpenes, or hydrogen sulfide and carbonyl sulfide. For the hydrocarbons, we would use a simple non-impregnated activated carbon, the EnviroCarb range in this matter, that effectively makes interactions with these hydrocarbons and retains them inside of its porosity. For hydrogen sulfide and carbonyl sulfide, you would need an impregnated carbon, as these molecules are too small to interact with the surface of the activated carbon. Now, important to note with these kind of molecules is that humidity, oxygen concentrations, and concentration of other impurities can have a profound impact, and different choices, different solutions will exist depending on the situation. Syngas in refineries, we can find as next to the hydrocarbon and H2S type of contamination. We can also find mercury as a contaminant, for which we have an activated carbon that we have been using already since the 1970s in refineries for removal of mercury down to nanogram levels. But next to that, there is also the iron and nickel carbonyl that sometimes pops up in the pre-treatment of syngas. And those two molecules are in fact very effectively removed on activated carbon. They're sufficiently large, and thus they are very effectively removed on this non-impregnated BPL type activated carbon. Now, next to the impurities itself to be screened, what is really important is to also consider the flow, pressure, temperature, and the rest of the operating parameters, because adsorption is not only a molecule that needs to get into the porosity, it will also develop a mass transfer zone, a little bit like in chromatography. So you will get a sort of wavefront that passes through an adsorber, and pressure, temperature, but as well flow rate can have a profound impact on the design of these adsorbers. So those are important points as well to take on. Now, next to this, I have here with me a small example of a removal of terpenes in sort of biosyngas application. So it's a system. You can see it's a little bit of a remote system. It was added onto a site where we have a flow rate of around 1,000 normal cubic meters per hour, a slight overpressure in the system. Ambient conditions, obviously, because everything is located outside in terms of the temperature. And because they started off as a new project, they were interested in using our plug and purify adsorbers at first. So we provided them with the larger one, the 80 meters cube Mach 4 unit. And this was for removal of mainly terpenes, but also some other organics from this biosyngas. Now, for that, we don't need any impregnated carbon, so we choose the EnviroCarb range activated carbon, a granular one, as it was compatible with the requested pressure drop, and it also provides for a better distribution of the flow. So in terms of the contaminants that were requested to be removed, we see that it's a very broad range going from C5 to C8 alkane type compound, as well as some traces of benzene, toluene, and then as well the terpene molecules that were identified. Now, as I already mentioned, these molecules, they will indeed diffuse into the pore structure of the activated carbon and be retained there. But by doing so, they will need a certain length in time or a length in path or bed depth to be effectively removed, a little bit like in chromatography, basically. Now, each of these molecules would need to do that. So we will get a sort of complex pattern of different mass transfer zones that would develop, and where also internal competition will come into play. So what we would do here is we would first look at the conditions that are presented by a project or a customer. And then we would make an evaluation about the sizing. And the sizing is not only done based on the adsorption capacity itself, because compounds like benzene and toluene, they would be very, very effectively removed on activated carbon, and the adsorption capacity is very high. But when we look a little bit deeper and we use our proprietary adsorption models, we basically would see that some of the molecules that would be very effectively removed would be, in fact, the limiting compound of the whole exercise. So here we can see that, for example, the pentane type molecule are present at the highest concentration, but they would only elute as the third compound out of our columns. And then benzene, which is present at very minute concentrations, is present at the lowest concentration, but it would be the limiting compound itself of the whole column. What we can also develop is that our pinene and limonene or terpene molecules are best retained and thus would not pose a limit to the system. So overall, we make the design to the most limiting compound, and thus we provide a solution for this kind of treatment process. In conclusion, activated carbon is a very versatile means for purification. A lot of different compounds can be removed. Either fixed adsorbers can be made, or people use plug and purify through mobile adsorbers. And quite importantly, we try to recycle as much as possible the used activated carbon to make a closed loop and to limit our CO2 footprint of activated carbon solutions. So I thank you very much all for your attention, and please feel free if there is any questions or remarks to get in touch with me either later on or even later on through email or telephone. Thank you.
Okay, thank you, Timothy, for your interesting talk. There are already some questions in the chat. First question, what happens to the contaminants absorbed in the carbon when it is recycled? H2S, for instance, is it broken down to elemental sulfur or released as OX?
It's not released. H2S, it depends on the concentrations levels itself during the recycling process, but they are basically reconverted to SOx, and these SOx's are then removed from the flue gas stream.
A second question, what interaction occurs at the surface of the coal during adsorption? Is it hydrophobic interaction?
It's hydrophobic van der Waals interactions that take place, yes.
A third question, what should be the mesh of a dust filter before an activated carbon adsorption system to avoid filling up the pores with fine dust?
That's a tough one. That really depends on a case-by-case evaluation, but overall we would recommend that nothing fine or 10 microns would be a good cutoff area. Sometimes 50, but let's say between 10 and 50 overall. But it's something that requires a little bit more deeper, detailed look into than just a common number.
A fourth question, can you comment on the efficiency of siloxanes removal using AC in the presence of H2S?
Yes, siloxanes are a very broad range of molecules. You have the 3-methylsilanol, which is a very small molecule, but you also have much larger siloxanes. The much larger siloxanes are very effectively removed on carbon because they can make a lot of interactions. The main culprit in difficult siloxane removal is the 3-methylsilanol because it's a small polar molecule. What we see is that these competition effects that I've shown in the example, they take place as well between H2S and siloxanes. So if there's a lot of H2S present, and although it might not be necessary to remove it down to zero, we need to take into account competing effects that will occur, and sometimes a little bit of H2S removal further down is necessary. But again, it's these kind of simulations that will need to be run to make it a very precise answer, but we can do that, yes.
Okay. A fifth question, could you think of an impregnation that would adsorb the benzene and MEK better, that would make better use of the column?
No, because normally the benzene and the MEK, they are very effective adsorbed on activated carbon itself. The structure of benzene is one single aromatic ring, whereas these graphite platelets are made out of hundreds, thousands of these aromatic rings. So the interaction is really very strong. The problem in the example that I wanted to highlight is that you also have a lot of other contaminants, and you need to take into account the overall gas stream that needs to be purified. So it could be that you find a contaminant that's a nuisance to a certain project, but it's the other contaminants around it that maybe do not pose directly an issue, but these also affect the adsorption capacity. So yeah, but there's no really other impregnant that we could think of or would think of for benzene or MEK removal. On itself, it's very well removed. If the pentane fraction would not have been present, we would have had a very high adsorption capacity for benzene, probably.
Okay, and last questions. Do you have any high potential activated carbon for biogas separation? And how do you comment about carbons deactivated from polymeric precursors, derived from polymeric precursors or roots?
That's a very long question. Separation through activated carbon is not really something that works well, and we would recommend doing that. For that, you could either use molecular sieves or membranes that are very effective in doing that, whereas activated carbon is not in separation of gases because of its vast porosity range. The second part of the question, activated carbon made out of depolymerized or other kind of raw materials is being looked at, but today the issue still is that you need a certain skeleton density, a certain porosity in the raw material itself in order to develop an activated carbon that's applicable to a broad range of uses. And that, to date, is not yet really available on depolymerization or other type of materials. There exist some synthetically produced activated carbons, but today still the cost of producing them is roughly a factor 5 to 10 more expensive than the conventional manner. So a little bit of work still ahead on that field.
Okay, these were the final questions. Thank you again, Timothy, for your interesting talk. And we will now move on to the next speaker. Our third speaker today is Professor Georgios Stefanidis from Ghent University. Professor Stefanidis is specialized in the broad field of process intensification, mostly focusing on alternative energy forms and transfer mechanisms, which mainly entails microwaves and plasma. His research activities include modeling of simultaneous occurring flow, chemistry, and multi-scale transport phenomena in electric, electromagnetic, and plasma fields, as well as design and development of tailored equipment for microwave and plasma-assisted reaction and separation processes, including, amongst others, CO2, methane, and biomass valorization processes. So, Georgios, the floor is yours.
Yeah. Okay. Well, the title of my talk is Microwave Plasma Gasification of Biomass. So there are two parts in it: microwave plasma and gasification. I like microwave plasma more than gasification. This is that's important for the audience to know, which means that I approach the process more from the technological point of view. As Elizabeth mentioned, I work in the broad field of process intensification, and I'm focusing on alternative energy forms. It's mainly microwaves and plasma, to a lesser extent ultrasound and light, and I look into how these technologies can intensify certain chemical processes and under what conditions. And gasification of biomass is just one of the processes that we have worked with. That said, you should expect a lot of comments and information on technical aspects related to plasma itself. Okay, when it comes to gasification, as also Kevin mentioned at the beginning, there are different types of gasifiers, fixed bed gasifiers, fluidized beds, vortex gasifiers. But I feel the most relevant gasification process to plasma-assisted gasification is entrained flow gasification, which is mainly applied for coal gasification. Most relevant in terms of the high temperatures in entrained flow gasifiers and the short contact times that are applied. But to attain this operating window, the entrained flow gasifiers work at high pressures, and also they require a pure oxygen source to elevate the temperature, and there is also intensive feed pretreatment applied, so the coal particles that are fed into the gasifier are quite fine. Plasma gasification has the particular feature of decoupling basically the energy that goes into the gasifier from the composition of the gasification agent and the feed itself. So the temperature does not depend on the temperature inside the gasifier does not depend on the composition of the materials that are fed into the gasifier. It's an allothermal process, and this gives the possibility of doing the process at very high temperatures and have complete gasification. It's also a technology which is robust to variable feed composition. And the fact that we can decouple the composition of the oxidizer from the energy that is produced or that is fed into the system also gives some flexibility with respect to tuning the composition of the product. As you're going to see also later, it's a very fast responding process, so the time to steady state is really fast. Now, when it comes to plasma gasification in particular, there are different types of plasmas. Of course, the most mature one that has been applied for gasification is thermal plasma, and that you should understand as plasma being in thermal equilibrium, which basically means that all the species inside plasma have approximately the same temperature. The system is in thermal equilibrium. So the degree of ionization is very high. The electrons that are generated get a lot of energy, which they transfer to ions and neutrals, and eventually the system comes to thermal equilibrium. But that results really in excessively high temperatures. So in the core of the plasma flames, you may have temperatures which well exceed 10,000 degrees Kelvin. So the temperature is really way higher than what is needed for gasification. And this is that's not a good thing. Also, it's a process that involves electrodes, which have a relatively limited lifespan. They need to be replaced frequently. That requires quite some maintenance. And also, the product is contaminated due to frequent electrode erosion. Also, quite some electric energy is dissipated into heat, not inside the reactor, but inside the hardware itself, which limits the overall energy efficiency. Nonetheless, this is still today the most mature process for this, the most mature technology for this kind of process. Back in 2010, what I'm going to present today is basically work that was done at the University of Delft, mostly in the period 2011, 2016, 17. And it was funded by different projects, starting from the Bill and Melinda Gates Foundation, and then partly by a European project, and then by Clariant. We were not working continuously over 5-6 years on this process, but at intervals we were revisiting this project, and we were trying to improve our microwave plasma gasifier, which was really, I think certainly the first one that was developed in Europe, and one of the first ones, I think, worldwide. When I wrote the first proposal in 2010 on microplasma gasification, there was really nothing in the literature in this process. What was the motivation for applying microwave plasma to gasification? Well, it's a process that does not involve electrodes. So in principle, that would require less maintenance, and also the plasma is supported by an alternating electromagnetic field, which means that electrons are continuously accelerated and decelerated, so they never get the very high energies and temperatures that they get in thermal plasma. And so consequently, the energy that they impart to ions and neutrals is less, and the system does not result in thermal equilibrium. So, of course, this is very hot plasmas you're going to see, but you don't have these excessively high temperatures that you have in thermal plasma. And also the conversion efficiency of electricity to thermal energy can be quite high. Overall, if the design is good, can be higher than 85%, so higher than in the case of thermal plasma. So that was the basic motivation, these reasons for us to start working on this. Of course, there are also some challenges and many technical limitations that I'm going to discuss later. The technology is not as mature as thermal plasma. The design of these gasifiers is very complex. There are actually no established design rules for microwave plasma gasifiers. The same applies to thermal plasma gasification, but the experience with microwave plasma is even less compared to thermal plasma. Another important limitation still applies today is the maximum power that one can get from a single magnetron, which is 100 kilowatt if we apply continuous delivery of power. If it is pulsed, it can go up to 500, 600 kilowatt, but for continuous power delivery, it's up to 100 kilowatt. It's an expensive piece of equipment. The price 3-4 years ago was let's say 1,000 euro per kilowatt, and of course the scale up is challenging. You can do it theoretically in 2 ways, either by lowering the frequency of operation or by combining several magnetrons and feed their energy to a single reactor. But again, there are technical limitations to be overcome here. I'm going to briefly discuss these 2 approaches at the end of the talk. So what did we do? Well, we did several experiments, but in this talk I'm going to basically focus on microplasma gasification of a side stream from a fermentation reactor that contains well, several things. You see here sugars, lignin, water solubles, acids, proteins, and ashes. It's a waste stream that cannot be chemically valorized, so it better be gasified to produce syngas, and from syngas other added value chemicals. The elemental composition is carbon, hydrogen 1.5, oxygen 0.49 for the results that you're going to see. These samples basically were provided to us by Clariant, and the analysis was done by them too. So this is the setup that we had developed at the University of Delft. The main part is this one. It's the microwave part of the equipment. So on the right side you see the magnetron. It works up to 6 kilowatt. It delivers continuously microwaves through this waveguide into the reactor assembly that sits here. On the other side, there is a movable reflector wall that tunes the field such that we create a resonant field with 1 field maximum inside the reactor where gasification takes place. There are some impedance tuners here in order to minimize the power that is that goes back to the magnetron. There is an isolator here in order to absorb whatever power cannot be contained inside the system by the between the reflector and the impedance tuners. On the top you see our feeding vessel, and yeah, this is the reactor assembly. I'm going to discuss some components in more detail. Process-wise, the carrier gas together with the biomass particles are fed from the top inside the tubular reactor. The diameter is 3 centimeters. The length about half a meter. Ignition takes place here, and the plasma flame points downwards. As you see here in the schematic, how do we ignite the field? We insert an ignition electrode, basically a sharp metal object inside the waveguide. This contracts the field. It creates a first spark. The spark absorbs microwaves and it grows into a stable plasma flame that is shown here. And at the same time, we really have to keep this flame away from the reactor walls in order to, for safety, for stability of the process. So somewhere here we have two nozzles that also give portion of the gas tangentially, such that a swirl flow is created between the flame and the reactor walls in order basically to seal the walls from the flame. Both the carrier gas and the swirl gas comprise nitrogen and air. And at the end we get the syngas product, which we measure, plus the ALSYs and the TARs, but we only measure the basic components of the syngas. As we were doing that for first time, all of our energy and our focus was on making this work stably, at least in some operating window, to give the proof of concept. Yeah, this is the feeding vessel and the screw feeders that we were using. Single screw feeder and double screw feeder to be able to provide coarse and finer particles with this one stably into the plasma flame. This is a picture of the reactor assembly. Basically, there are two parts. It's the upper part where ignition takes place. So the upper part of the reactor is inside the waveguide. You see some viewing holes. All this was custom designed, by the way. So we were applying here pyrometry and optical emission spectroscopy in order to probe the temperature of the wall and the temperature close to of the gas close to the ignition point. This is our optical spectrometer. The entire thing is, and I will explain that, cooled with water flow from this height downwards. This is the exit of the reactor. You see here the cooling manifold. When we do reactive experiments, then the whole thing is placed in a drum, and at the bottom we collect the ash, and then the syngas product goes upwards and towards the backside of the reactor for further cleaning before we measure the composition of the syngas. This is the reactor assembly, the materials that we were using. So the reactor itself comprised basically three main layers. The inner one is the quartz or borosilicate reactor. These are the two materials that we used. They don't differ too much. Then we have brass plates around the quartz or borosilicate tube in order to more effectively remove the heat. And then there is a layer of stainless steel for support, and then this is the cooling manifold. As I mentioned, the whole thing is cooled by water flow. And then at the back side of the reactor, yeah, this is the reactor. Here we have a cell and tube heat exchanger, and then a cyclone it's here to remove unconverted solids and ashes that were not collected at the bottom of the reactor. And then we have two plate heat exchangers. Well, in one of them, the hot syngas is cooled down by the cold syngas by the second heat exchanger, and the syngas in the second heat exchanger is cooled by ethylene glycol. And then we have very briefly the gas conditioning section that comprises 4 filters: activated carbon, filter with calcium oxide, a 10 micron and a 2 micron filter to eliminate all moisture, solids, and contaminants before the gas got into the sampling section. So we sample part of the gas and the rest goes to flare. So this is briefly how the setup looks like. Now a key issue is in this process is the distribution of the heat fluxes and the temperatures inside that system. That significantly affects not only performance but also the stability of the process, and it's a challenge to measure temperatures inside the system. We do the thermal analysis doing non-reactive experiments, so we just feed air and nitrogen. We cannot do that while the process itself, the gasification process itself, is running, but that way we get a feeling of what temperature levels we have inside the reactor. So these are the conditions based on which we do the thermal analysis. We have to keep the temperature of the wall inside the waveguide to 500 degrees Celsius. Unfortunately, I'll explain why, because we need to, that limits the performance of gasification. But to keep the temperature at this level, we have to withdraw a lot of heat throughout the entire length. So we measure temperature with the thermal camera on the outer surface of the reactor. We measure temperature at the outlet of the reactor and some 10 centimeters above the outlet. This is the temperature level around, let's say, 900 degrees C, 1000 degrees C. We use a pyrometer to measure the temperature at the wall of the reactor inside the waveguide close to the ignition point, where the temperature of the gas is expected to reach its highest values. We use optical emission spectroscopy to record gas temperature near the ignition point. So you see the temperature level. at the representative power level at which we do the experiments, and you're going to see the results. And we use also a heat transfer model in COMSOL without flow to calculate heat fluxes such that they match these temperatures that we measure in the domain. And the important thing from this analysis is shown here. No matter what material we use, we have to remove only in the lower part of the reactor some 40 to 45% of the total energy that we put into the system in order to be able to keep the wall temperature inside the waveguide limited, because otherwise things like this happen. So it's here where we want to keep the temperature stable. I would say less than, we keep it to 500 degrees Celsius. It certainly has to be kept less than 600 degrees Celsius. What we observed is that when the temperature goes higher than this value, then the temperature of the wall rapidly increases up to the melting point, which is 1700 Celsius. We would expect that cores would be able to stand these temperatures, but what I think was happening is that the dielectric properties of quartz at these temperatures change, and then it's the wall itself, which is otherwise meant to be transparent, starts absorbing microwaves, and then yeah, the temperature, we have a runaway phenomenon. The temperature goes to the melting point. And of course the process is shut. But even without this problem, we have also stability problems, material stability problems downstream, even near the outlet of the reactor, when we heat and cool all the time due to the thermal shocks, or when we don't tune the flows properly and we have the flame touching the wall. Or when the temperature of the flame goes too high, then we have initially this swelling and then eventually breakage, and we had to kill actually tens of reactors due to thermal failures. So thermal failure and the significant heat losses, to avoid them is two important problems. The third main technical issue was the deposition of tars and solids on the walls. You don't want to have that. First, because okay, part of the material is not converted, but other than that, when you have deposition of carbon on the walls, then that prevents penetration of microwaves inside the flame. So microwaves are dissipated where you don't want them to be dissipated, that is on the reactor walls, and then you have the phenomenon that I described before. So some results with that feedstock that I mentioned. This is the composition of the elemental composition of the feed, as received on dry basis and dry ash-free basis. It's here. Basically, what we wanted to do was to identify an operating window for stable operation and for high performance. And by high performance, we mean in that case high carbon conversion efficiency and high cold gas efficiency, which in the case of plasma is defined by that ratio. And in the numerator, you have the LHSV, or lower heating value of syngas, and the denominator, it's the lower heating value of biomass plus the power that is consumed by the magnetron. Well, this is the particle size distribution for the results that I'm going to show. So the particle diameter is up to 1 millimeter. You see the characteristic D10, D50, D90 values here. We also did experiments with finer particles. I'm going to present the results for the coarser ones, which were those. Yeah, very limited operating window. Stability of processing in this type of reactors is a bottleneck still. So this is the base case, the flow, the direct flow that carries the biomass down the reactor, the swirl flow, and the air to nitrogen ratio. So here in experiments 2 and 3, we keep the direct flow constant and we vary the swirl flow. In experiments 4 and 5, we vary the ratio of the direct and the swirl flow, and we keep the total flow constant to 35 normal liters per minute. The biomass feed rate was quite low, 0.1 gram per second. We can get the same performance with 10, 20 times higher biomass flow rates. That's possible. We have done that, but the process is less stable, possibly because we feed through the ignition point, and when we increase the flow of biomass too much, that disturbs the ignition point and the process start. Maybe it would be a better idea to feed from the side, but as I explained, okay, this is that was the first effort of that kind. So you see here the Syngas composition. It's a very limited operating window. So the composition in terms of carbon monoxide, carbon dioxide, and hydrogen does not change too much. And the same goes for the conversion efficiency and the cold gas efficiency for most experiments. In the best case, we got which is case 3. Here, so direct flow 5 normal liters per minute, swirl flow 20 liters per minute. The cold gas efficiency was a little bit higher than 40%, and the carbon conversion efficiency was close to 90%. But recall that most of the 40% higher than 40% of the energy that we put into the reactor is withdrawn only in the lower part of the reactor in order to keep the world temperature bounded. Yeah, we wanted to see how close the composition of the syngas is to equilibrium. So we defined a very simple equilibrium model, non-stoichiometric, homogeneous. While several of these coefficients can be calculated from the operating conditions. And then, for example, from the moisture content, from the equivalence ratio, from the type of gasification agent, and from the air to nitrogen ratio, the remaining coefficients are calculated from, well, they can be calculated from the elemental balances, and we also assume that the water gas shift reaction is at equilibrium. So we have 5, I think, remaining coefficients and 5 equations to solve to calculate them, the 4 elemental balances and the equation that defines the equilibrium constant for the water gas shift. In our case, we did not take into account methane steam reforming. We set this coefficient to 0. The methane that we measure in our experiments is less than 1%. Yeah, to keep it more simple, we set that to 0. That's how we define the equilibrium composition, and we calculate it as a function of temperature over the temperature range that we believe, based on the temperature measurements that we do at certain points that I explained, we have inside the reactor. Yeah, the dust lines indicate the equilibrium predictions. The colored zones is the range of our experimental data for hydrogen, for CO, for hydrogen, and for CO2. And the points here basically they are the same in all temperatures. They represent case 3 of this table. What I think is that our equilibrium, well, our outlet composition is not far from the what is predicted by equilibrium, at least for the range of temperatures that we have inside the reactor. But unfortunately, we spend a lot more energy than necessary in order to have the temperature conditions that we need for gasification because of the heat losses. The final slides are devoted to scale up and what should be done to also make the system more adiabatic and that by that way more efficient. There are two approaches, as I mentioned at the beginning of the talk. One approach is to lower the frequency of operation. We operate this is essentially a lab scale gasifier. It operates at 2.45 gigahertz. We can decrease the frequency 3 times and work at 915 megahertz. Then the system would look like that. This would be the microwave generator. This is the waveguide. We would place the reactor here, and this is the holder for the reactor, and this is the reflector. In that case, the diameter of the reactor would go from, let's say, 3 centimeters to 10, 11, and the length would be about 2 meters. So the entire volume would increase by 30 times. And with that system, we would be able to apply the maximum available power for the magnetrons that are on the market today. That is 100 kilowatt. Yeah, so 30 times larger volumes. But I feel this is the limitation of this approach. In this approach, essentially, we make a resonant field and we place the reactor in the resonant field, but eventually the size of the reactor is limited by the wavelength. The alternative approach, I think, is implied in that paper, which I usually show in my presentations, although it's not our work. It was presented by a Korean group in 2014. Strangely enough, although this is there's a great performance reported here, there was no follow-up, and also no design details are given, and I think I could not find a relevant patent either. But it represents the alternative approach, which I think is the future for this type of systems. Instead of, as I said before, making the field and placing the reactor in the field, you first make the chamber and you design the flows as big as you want in order to have the necessary throughput, and then you feed microwaves inside such a vessel by different magnetrons. You can use many through open-ended waveguides. So you make the chamber and you throw microwaves in there. And of course, as I said, the design details are not given here. But you see the size of the system is quite high. The diameter is 90 centimeters. The height is 180 centimeters. It's a 500 kilowatt thermal microwave plasma gasifier. The cold gas efficiency is quite high at the level of entrained flow gasification. Of course, they also feed very, very fine powders of brown coal. Yeah, I think that in such a system, of course, it should be studied such that yeah, the flow should be studied properly in order to have efficient gasification. But if one manages to thermal insulate that system, then the temperature would be sufficiently high everywhere in the domain in order to have efficient gasification. That itself would be a big step towards commercialization of the process. You see what they report in that paper is they use high alumina castable for internal wall material, and this is insulated by a cement layer. And that way they claim to be able to work at inner wall temperatures at the level of 1700 degrees Celsius. And of course, if you have such high temperatures of the walls, then yeah, conversion efficiency can be quite high, and the cold gas efficiency will be very high as well. So I think this approach is the future. Strangely enough, there hasn't been any follow-up of this paper, but yeah, this is the approach that I'm now trying to implement next to modeling, setting up a model for microwave plasma gasification that would combine yeah, the flow equations, heat transfer model we have already, but we try to couple it with the flow model and some global kinetics for biomass gasification. Okay. I think in view of the time, yeah, I better stop here. Yeah, you have presented the results. Our experience from several years of work on this process is that there must be progress on the materials, on insulating the reactor, or that holds also for other types of plasma gasifiers, and developing models that combine kinetics, flow, and heat transfer to be able to design these systems properly and optimize them, because all we do, actually all groups that work in this field, is almost purely empirical at present. Okay, thank you very much.
For your presentation. I will first word to Kevin to ask some questions.
Very nice presentation, Georgios. I also wanted to have a bit of your feedback on something else that we are working on. This is the Smart C project that we are working on together. And that's basically about CO2 utilization. So where we have the super dry reforming process developed in Ghent for converting CO2 in CO. Also there, plasma can play an important role, as shown here on the slide. What do you see there as the best plasma technology that could interact with super dry reforming and for example waste streams like plastics and so on?
Well, I guess plasma can be used two ways: either to gasify carbon with CO2 and make a stream of CO, which is needed for the basically a stream of CO and CO2, which is needed for the super dry reforming process, but also for gasification of plastics. Yeah, do you want to comment on the process only that plasma can be applied to, or the?
Well, so here specifically, so here we have like a plasma torch. Do you believe there that this is the right technology to interfere with these kind of processes, or do you see other possibilities for plasma here to interact with these kind of CO2 converting processes where they typically try to combine it with biomass or plastic waste? Yeah. So is plasma torch the right way or not?
Primarily to plastic waste, I think, and gasification of carbon with CO2 to make CO, because I think carbon is a byproduct of the steel mill, or not? Yeah.
Yeah. It is,
yeah. So these, yeah. Yeah, the main limitation is the scale up of the process, but I believe that by combining magnetrons of many magnetrons that feed their power into a single reactor unit can solve this problem. But again, yeah, this is not at commercial level yet. It has to be developed. But I think it's feasible. And you want to, I think this is the main advantage compared to thermoplasma. As I understand, you don't need to have these extremely high temperatures that you have in thermoplasma. And the conversion efficiency of microwaves of electricity to heat eventually can be quite high, because we'll be working at 950 megahertz. At this frequency, conversion of electricity to microwaves is higher than 85%. And then if you design the system properly, microwaves can be fully 100% dissipate into heat inside the reactor. You don't have that in thermoplasma. The conversion efficiency of electricity to heat, I believe, is less than 50%. The hardware even consumes, I think, a lot of energy, even at idle mode.
Okay, thank you, George. With maybe some venture capital, we could actually make this work, or if the EU approves it. Thank you for a very nice talk. Okay.
There are still a few questions in the chat. First question: how do you control the amount of oxygen needed for the gasification? I understand that the temperature is controlled by the amount of energy to the microwave torch independently.
Yeah, in that, I think I had it in one of the slides. We picked an equivalence ratio that is in the range of what is used for gasification. So in our case, it was 0.4, the equivalence ratio. It can be lower. Yeah, it's indeed independent. We did not do a broad parametric study as to the effect of oxygen content, but yeah, you can increase, for example, the amount of nitrogen that you put in and decrease the amount of air, and that would vary the amount of oxygen, and still you would have the same temperature levels inside the reactor. So this is possible. Now and this gets back to what I said before, that the process is still not optimized. We still get oxygen at the outlet, although we're not supposed to. So because there's a lot of oxygen in the swell flow that does not gasify any biomass, so you get it at the outlet. Knowing that we still have oxygen at the outlet, we did not try to decrease the equivalence ratio, but there is flexibility as to the amount of oxygen that is put into the system. Yeah.
Okay. Second question: what is the lifetime you expect with the microwave plasma torch?
Well, if you're able to insulate the reactor such that it stands the temperature that developed in the system, the process can I don't see any other major limitations. I mean, these experiments that I showed, we were able to run the experiments, okay, for an hour or so without problems. The problem starts when the maximum allowable wall temperature exceeds a certain limit, and then you have this phenomenon that I mentioned of the wall itself starting absorbing microwaves. But if you control the system such that the wall temperatures are at the level that keep the material stable, then yeah, the process can run. I don't see another limitation as with the case of electrodes in thermal plasma.
Okay, thank you. And then the third and last question: is the dilution from the carrier gas, etc., acceptable for a scaled-up process? Is there a strategy to address this?
The dilution, sorry, I couldn't hear that.
Is the dilution from the carrier gas, etc., acceptable for a scaled-up process? Is there a strategy to address this?
I don't feel that there's a dilution of the. I mean, in principle, we should be able. That's also a motivation of using microwave plasma to use less diluted. To have a less diluted syngas when you apply microwave plasma, exactly because you decouple the power level, well, the energy that you put into the system and the temperature from the oxidizer. So in principle, we should be able to work at lower equivalence ratios compared to and use less oxidizer compared to the industrial process. I think this is an advantage of the of using plasma in general, not a disadvantage. But as I said, in these experiments, basically we did a very limited parametric study because our focus was to show that the technology works. It was really the first gasifier of its type that was developed at lab scale, microwave plasma gasifier.
Okay, thank you, Georgios, and thank you again for your interesting presentation. This brings us to our final speaker for today. Our fourth speaker is Benoit Carthuizer from CERTECH, who is also a partner in the PSYCHE project. Benoit graduated as a chemical engineer from the University of Louvain and obtained a PhD in chemistry, more specifically catalysis, at the University of Limerick in Ireland. Since 1996, he works at CERTECH with focus on inorganic chemistry. He was involved in the treatment of xylene by catalysis oxidation, the development of hydrophobic coatings, and air treatments by photocatalysis. For the latter, he was a Belgian expert at the CENTC 386 photocatalysis committee. Benoit, the floor is yours.
Okay. I will give you some information about the high temperature syngas purification. as it was already explained in other presentation, that gasification is a very good alternative to for the valorization of different type of carbonaceous materials like biomass, coal, municipal waste, plastic waste, and so on. The main composition of the syngas are hydrogen monoxide, carbon dioxide, some water, and also some impurities that needs to be removed from the syngas if you want to use it in other processes like the Fischer-Tropsch. The different type of impurities are summarized in the tables here. You have some sulfur compounds like H2SO that we already speak about. And the problems that we could have on the different processes is that there's a corrosion of the system. Also, if they are just released to the atmosphere, it's just pollution of the atmosphere. We could find some highlights, hydrogen highlighter compounds, HCl, HF, and so on. Some metal carbonyls that also there is problems of deposition that can block the systems. Some nitrogen compounds, of course, there's problems on the emission on the environment if they are not removed. We could find some heavy metal like mercury, chromium, zinc, manganese, some tars, also some particles, some CO2, silica, some ash. There is problems that they can also can deposit in different places and downstream systems that needs really to remove. Also, those impurities come from a different types of starting materials, and then it's quite difficult to have only one process for any type of syngas systems. Or can we clean up the syngas? Actually, there are two ways to remove the impurities. The more well-known one is the cold gas cleaning process. It's a very well-established system for the purification of a syngas, but the problem is that we need to cool down the flow to low temperature, even sometimes like room temperature, but needs to have some heat exchangers in different places. And also they are usually using some water or some solvent to remove the impurities. That needs to have another process to clean up those byproducts that involve to increase the space to clean up the syngas. In the hot gas cleaning processes, that's SGC, actually we can work at higher temperature than the cold gas. That needs we don't need to have some heat exchanger to control the temperature. Also, it will be possible to have some regenerable sorbents, then that involve less byproduct to be treated afterwards. But it's not a very well established syngas purification, and it's still on development. We could find on pilot scale experiments. The different step for the cold gas cleaning system actually is cooling, like I said already, cooling the gas at the right temperature for the treatment. Usually there is a pyramid dust removal, so filter or cyclones. There is a unit of scrubbing to remove the alkali, the halides, the particle stars. Usually there is an absorption unit for H2S. That involves some amine solution or methanol or polyethylene glycol and so on. Often, if there is some serious presence in the syngas, it's necessary to actually produce some H2S, because usually COS is very not well absorbed in different types of solvent. And if some mercury are present or other type of heavy metals, we're finishing actually with some activated carbon, which can be also very active for the oxide. For the dry syngas purification, higher temperature. Actually, the ash and soil particles can be removed using high temperature filtrations, like a ceramic or metallic filter. Of course, there is a waste of just the particles. The sulfur compounds can be removed by using some metal oxide sorbents that I will come back later on. The hydrogen halide also can be removed at higher temperature with some alkali metals or alkaline earth metals. There also there's some waste that needs to be removed and treated. Metal carbonate can be decomposed by a catalytic process. Nitrogen compounds that we can use at the Genox process, which is quite a well-known process. And heavy metal that actually are condensed in either activity carbon at low temperature or possibly using some copper oxide sorbent to work at higher temperature. And tars can be removed either by thermal cracking, catalytic cracking, or condensation, or just with scrubbing. This is an example of a flow process to remove to clean syngas at higher temperature. Then, if necessary, we have some mercury removal process, some halide removal process, and some air sulfur removal process, and then can be finishing by a filter before starting going in the downstream process like Fischer-Tropsch systems. I will have a look more detail for the halide removal and the sulfur removal, and also quickly the mercury removal. In the case of the halide removal, actually, Kabayashi developed some sorbent made of aluminate sodium systems, which can react with the halides and to produce a salt. This salt has to be removed. The major difficulty they got it was to be able to make some pellets of those aluminate sodium. Then they have a special formulation that they managed to make those pellets, and they were able to work actually around 450 degrees, and this is a curve of the high throughput breakthrough curve, and it's very important actually to know the point where the pollutants start to be detected again in the gas phase. And this it's important to have it to dimension the process. In this case, it's not possible to actually to regenerate the pellets, and that's a waste. In the case of the dry sulfur removal sorbent, actually, metal oxides are very good candidate to remove the sulfur compounds. They're reacting with the oxide to produce sulfur metals and water. And the regeneration is made by oxidation of the sulfur metals to produce the oxide and SO2, which actually is capped. Some candidates are the zinc oxide, copper, nickel, and cerium, which can remove the H2S at lower than 10 ppm, even at a ppb level. Other compounds like iron, calcium, or manganese could not be as effective, and then if you need to have very, very low concentration of H2S in the syngas, it's quite, they will not be able to work it. This actually, the Kobayashi worked also on the sulfur removal process, and they developed a sorbent based on the zinc ferrite systems, and they managed to make a honeycomb support, which is actually also the catalyst that we can see. The process for the removal of the sulfur is actually in 3 steps. It's a cycle. A first step that we can see here is the removal of the sulfur compounds by the zinc ferrite systems, forming some sulfur, zinc sulfur and iron sulfur. Then there is a regeneration of the sorbent by oxygen, then produce SO2, which actually then are capped. And then there is a last step, the third step, that is to have a reduction on the zinc ferrite system. Actually, is that the compounds which is more effective to remove the sulfur systems. That means it's a cycle. Then we can do as much a cycle as necessary to work for a long time. This is an example of how works the cycles. Like if we're taking the first reactor, the A1, on the first step, it does the sulfidation steps until there is we can start to detect some H2S or CO2S in the gas phase. Then it does the second step where there is a removal, the regeneration, then there is a production of SO2, and then you can see oxygen passing through. Then that means there is the regeneration is over, and the last step is the reduction of the sorbent. Then it can start again the cycles. And they were working around 450 degrees to remove the sulfur. This is an example of breakthrough curve that we got at CERTECH with some zinc ferrite that we synthesized in CERTECH. Okay, the condition were not the same as we saw previously. We were working at lower temperature because my oven at the moment could not work at higher temperature, and also it's not it's just H2SCOS on nitrogen and not in a reduced condition, which is less active in that cases. But we can see that for H2S starting from 230 ppm, we managed to remove it, and for quite a long time. This is just only 70 milligrams of the solids, and then you can see the breakthrough. It's less effective for COS, but the concentration of SOS is quite heavy, very high in comparison of what you can find in a real syngas composition. From this curve, it's possible to dimension a reactor to know after so much time we need to pass for the regeneration step and for the reduction step. Finally, the last development they made, it was a development of a mercury removal sorbent, and it was based actually in a copper oxide sorbent. Also, they just coated an honeycomb systems with the copper oxide, and to be very effective, the first step of the copper oxide sorbent is to have sulfidation of the copper oxide to produce some copper sulfide, which is the more effective to remove the mercury. Then there is a reaction with the copper sulfide and the mercury to produce mercury sulfide, and this is the mercury, the sorbent is regenerated at a higher temperature with oxygen and produce some SO2 and mercury can be concentrated then in some well-known system like activated carbon. This is an example of some breakthrough curve of three cycles of mercury removal, and what we can see is that while increasing the number of cycles, there is a long breakthrough is increasing also. They explain that just because by it stabilizes the copper sulfide on the surface of the sorbent, and that's increased the capacity of the systems. In this graph, they're just comparing the mercury uptake from the gas phase with the mercury release during the regeneration step, and there is quite a good correspondence between both steps. That means that the system can be regenerated and reused again for another cycle. Just to finish it with a figure to summarize the mercury removal sorbent procedure. The first one is some sulfidation of the copper oxide. Then there is removal of the mercury on the surface of copper oxide sulfate. And then there is a regeneration with some oxygen, nitrogen, and there is a high concentrated mercury which is condensed in, for example, activated carbon. And the cycle can start again. The advantage is that it works with a low flow of air, and that means that there is a very small amount of flow needs to be cooled down to be very effective with the activated carbon condensation, which is not the case if we started directly with the syngas, that we have to cool down a large amount of flow. In conclusion, that for the dry cleaning system for syngas, that there is some interesting work be done on dry sorbent purification, like for the halide removal with some aluminate-based sorbent, which actually produce some waste. The regenerable zinc ferrite-based sorbent for H2S and COS removal, and also some copper oxide-based sorbent for mercury removal. With for the H2S and COS removal, actually all the metal oxide could be used, but the problem is the temperature of the regeneration system, that often the temperature is much higher than what we got with the zinc ferrite-based system, which is interesting cases. There is still a lot of work to be done to pass from the pilot scale to the industrial use. The advantage of the dry cleaning process is that we don't need to cool down the syngas flow at a very low temperature. And there's some interesting over there. There is no wastewater treatment that we could find in the cold system. Also, there is a possibility to remove the halide impurities at higher temperature, and it's possible to remove some sulfur and mercury on different types of sorbents. Thank you very much. That's the end of the presentation.
So thank you, Benoit, for your presentation. To end, I would like to thank all the speakers for their interesting presentations and all of you for participating to this workshop. I would also like to acknowledge the funding we received from the European Regional Development Fund via the Interreg France-Wallonie-Vlaanderen program, together with funding from our local authorities, being the provinces of West and East Flanders, the Walloon Region, and the Walloon Public Service on Economy, Work and Research. So thank you all and have a nice day.